Hello. So, continuing the discussion on singular value decomposition. So, we have A equals to U sigma Vt. Now, I have asked to look further into decomposing U and V. So, the U and V are orthogonal matrices. So, let's take a look at the answer.
Yes, there are ways to further decompose the orthogonal matrices $U$ and $V$ from the singular value decomposition $A equals U sigma V caret T dollar, and there can be benefits depending on the specific application and the insights you are trying to gain. Here are some common ways to decompose orthogonal matrices and their potential benefits. 1. Decomposition into rotations and reflections. In 2D, the $2 times $2 orthogonal matrix can always be represented as either a rotation by an angled $theta dollar or a reflection followed by a rotation. In 3D, a $3 times $3 orthogonal matrix with determinant plus 1 represents a rotation and can be decomposed into Euler angles, e.g., roll, pitch, yaw, which are three separate rotations around specific axes. An orthogonal matrix with determinant minus 1 involves a reflection. Householder reflections. Any $M times M dollar orthogonal matrix $U$ can be represented as a product of at most $M householder reflections. A householder reflection is a transformation that reflects points across a hyperplane. Givens rotations. Similarly, any orthogonal matrix can be decomposed into a sequence of Givens rotations, which are rotations in a 2D subspace plane. For an $n times n dollar orthogonal matrix, you might need on the order of $ON squared, $Givens rotations. Benefits of further decomposition. Interpretability. Decomposing $U$ and $V$ into a sequence of rotations and reflections can provide a more intuitive understanding of the linear transformation represented by these matrices. For example, in robotics or computer graphics, representing orientations using Euler angles is often more natural than using a full rotation matrix. Parameterization. These decompositions often provide a minimal set of parameters to represent the orthogonal transformation. For instance, a 3D rotation can be parameterized by just 3 Euler angles, whereas a $3 times $3 rotation matrix has 9 elements with constraints. This can be beneficial in optimization problems, or when you need a compact representation. Computational efficiency. In some cases, applying a sequence of simpler transformations, like rotations or reflections, can be computationally more efficient than multiplying by a dense orthogonal matrix, especially if the...
Yeah, so these 2 points I find more interesting. Of course, all of them are interesting here. The parameterization, so roll, pitch, and yaw, that comes naturally for 3D, and with we can just represent with these 3. Whereas a 3 by 3 rotation matrix has 9 elements with constraints, and so that is also computational essentially. And there is this simpler transformations can be computationally more efficient when decomposing EU or V into a sequence of rotations and reflections, and it will not be like a infinite number of rotations or reflections. It's just it depends upon the number of the dimension. So for m by m we need at most m reflections, so there is an upper limit which is linearly dependent on the dimension. uh, Maybe you have to look into that if it can be reduced any further, but it is computationally definitely efficient.
Decomposition has a sparse structure, e.g., a small number of non-zero angles in Givens rotations.
Given
Specific applications. Robotics and computer graphics, Euler angles are widely used to represent the orientation of objects. Numerical algorithms, householder reflections are fundamental in algorithms like QR decomposition for numerical stability and efficiency. Signal processing and quantum computing, rotations in specific planes related to Givens rotations, are often used as building blocks for more complex transformations. Considerations. Uniqueness. The decomposition might not be unique. For example, there are multiple conventions for Euler angles, and a given orthogonal matrix can be represented by different sets of Euler angles. Complexity. The number of components in the decomposition can be large. For instance, representing a general $n times n dollar orthogonal matrix using Givens rotations requires $ON squared dollar rotations. Singular values already provide key information. It's important to remember that the SVD itself already provides a significant decomposition of the matrix $a into components related to the principal directions of variance. The singular values in $sigma dollar tell you the strength of the transformation along these directions, and $u dollar and $v dollar provide the orthonormal basis
there you go. Yeah, so I'll try more follow-up questions and some related topics as well. So I hope you guys enjoy it. And if anybody has any other questions to discuss, let me know please. Thank you.